What? Huh? This is the translator speaking. This is the most attractive speaker I've seen all day today. So you should all pay attention to him. Hello. So who makes the best asado? Well, I was going to say Uruguay, but then yesterday, or a couple days ago, we had this and that and that and that. So I'm sorry, I have to say Argentina. But I don't know. Another question I wanted to ask is like, what country has the best footballers? So when I was in Brazil, I said, "Oh, Argentina, absolutely Argentina." But then I came here and found out that, well, River is in national beef. So my name is Patterson. I'm on the internet as Tender Love, so you can follow me there. I'm on the Ruby core team, and I'm also on the Rails core team. But I have to warn you that just because I'm on those two teams doesn't mean I know what I'm talking about. So, you know, if you have questions, like, make sure to ask me. If we have time at the end, please ask me. And if we don't, just come up and ask me. I will answer any questions. It doesn't even have to be about asado or football or anything. Especially not football, since I don't know anything about it besides river status. But I'm really excited today. I'm very, very excited because I don't know if you noticed, but we're in Argentina, and yes, it's insanely awesome. Have you ever been to Argentina? This is my first time. But I'm also very, very nervous. Whenever I get on stage, I get really nervous, and I'm nervous today. And a friend of mine, Jose, that's Jose, he said to me, well, whenever you get on stage, what you need to do is just think to yourself, what would Freddie Mercury do? So that's what I think to myself. And I'm trying to think that now. So I live in Seattle, and it's in the United States and very, very far north near Canada, so we're not exposed to that much Spanish, so most of the Spanish I know is from the internet, or also from Mexican soap operas, and all that I could get from those is, "Por qué, Maria?" So that's all I remember. It's kind of awkward in cabs, because I'll say like, "This place, por qué?" And they have no idea what I'm talking about, and I get lost. Also, I think every street is like Claro Street or something like that. It's very, I don't know, it's hard for me to get around. So I want to say thanks to all of you. Thanks to all of you for coming. Thanks to RubyConf Argentina. You should give everybody here a round of applause. The staff members are amazing. So I want to thank you all. Thank you so much. So what I want to talk about today is resource management, and what I mean by resource management is kind of specific to Rails. Like, I want to talk about path management, like the paths, the resources that are in your Rails systems. And the things I'm going to talk about aren't specific to Rails, but you know, the ideas aren't specific to Rails, but Rails uses them. So we're going to learn some stuff that you know, isn't necessarily needed for Rails. Well, Rails needs it, but you don't need to use these ideas in Rails. So specifically what I want to talk about with path management is I want to talk about pattern matching. So we're going to take a look at pattern matching with regards to path management. And even if the concepts that I introduce here are like too hard, there's one thing, like at the very, you know, basic thing that you can take away from this talk is get this tool. GraphViz. It's an amazing tool. Once you learn how to use it, you'll end up using it for all of your projects. So GraphViz is a tool that it produces graphs like this, and the way that you produce this particular graph is you have a text file that looks like this. That's all it is. You feed the text file into the GraphViz program, and it outputs the previous graph that we saw. And we can even add nodes and edges. So here we have 3 nodes, and you can tell the shape, and then we have 2 edges, and it will produce this type of graph. But throughout the rest of this talk, we're going to take a look at graphs that look similar to this. You don't need to understand what it is. I'm just showing you the general, shape of it. And we'll talk about this graph as we go through. So we're talking about path management and like the paths that are in your system. And the reason I want to talk about it today is because I rewrote the Rails router, and it is called Journey. And yes, it's named after the 70s rock sensation Journey, in case you're wondering. So, well, the question is, what is a router? Let's define what a router is. A router has 3 responsibilities. The 3 responsibilities are URL generation. So when you say like link to in your Rails code, it generates the actual path that's in there. Path recognition, which is when a request comes in, it looks at the path and figures out what controller to send it to. And then the third responsibility is route parsing. So your declaration, like the declaration parsing. So everything that's in your routes.rb. So the router will actually take all the information that it processed from routes.rb and use that to deal with the other 2 responsibilities. So you might be asking yourself, why a new router? Why? And really the truth is that whenever anybody joins the Rails core team, they are required to rewrite the router. It's a rite of passage. So as soon as we get a new member, this thing will be rewritten. But really why I rewrote this router is for maintenance. One reason is for maintenance. And this graph here shows lines of code. The graph on the right is the original, or the bar on the right is the original implementation. The bar on the left here is my first implementation that passed all tests, and it was less than half the number of lines of code that the current implementation is. And that middle one is where it sits today, and that's adding some new features and improving performance and stuff. And we're going to take a look at some of the new features that kind of bump that up a little. So it's just a little bit over half the size. Another important reason why I rewrote it is I want to use known algorithms. If you read the source code for the current router, which is in 3.0 and 3.1, it's very difficult to figure out what the algorithms are that it uses for recognizing paths and generating URLs and stuff. And in fact, if you want to get more information about the stuff I'm going to talk about and the techniques I used, I just stole them from compiler books. So if you go take a look at these books, you'll learn all this information that we're going to talk about today. So another reason why I wanted a new router is predictability. So if we have these particular known algorithms that are implementing our router, we can say, well, how much CPU time is it going to take in order to recognize a route? How much CPU time is it going to take to produce a path? Things like that. And the other thing that we can say is, well, how much memory usage is this going to take? Like, given a particular routes.rb file, once we load that in, how much memory is it going to take in the system? So as far as performance is concerned, I didn't put any numbers on this graph because it doesn't really matter. What's important is higher is better. So currently URL generation and path recognition are about the same speed in Journey as they are in the current router. But we have a really large gain in route parsing. So your routes.rb file, Journey can process your routes.rb file about twice as fast as the current router can. So where that really helps is on boot time, although that's not the major reason that boot time is slow, but we should talk about that later. This will just improve it. So I like this gain in speed, so I added this slide. So let's take a look at patterns. We're talking about URL recognition and paths and stuff, and why patterns matter. Patterns matter because we use them every day. When we're writing our routes.rb file, we're actually writing out regular expressions. So it's important for us to understand the way that pattern matching works, because under the hood, that's really what we're doing with our router when we're recognizing paths, is we're just doing recognizing patterns. So if we take a look at Rails routes, and we see something like this in our routes.rb file, like resources articles, we'll notice that it generates 4 different paths, and they look like this. So these are the paths that we generate in our system, and most of you should be familiar with them. And these look very similar to regular expressions, but the main differences are, like, the parentheses in here, the parentheses don't capture anything. It just means that they're optional. That section is optional. And whenever you see like a colon foo or a colon whatever, it maps to this regular expression. You don't need to understand that regular expression. The important part is that it just maps to a regular expression. Now, what this means is we can actually take a path like this and translate it into a regular expression. So do a direct translation from the declared path in our routes.rb file into a regular expression. So if we take all 4 of those paths that we saw earlier and translate them to regular expressions, this is what it'll look like. So let's say we get a request. A request comes in to our system, get articles new, and we need to match this. Now let's pretend that all our router does today, let's pretend that what it does is it just takes each of those paths and converts each of them into a regular expression, so we just have a list of regular expressions that we match against. So the way that'll work is, the request comes in and then the router says, okay, does it match the first regular expression? And then it says, oh no, it doesn't match the first regular expression. So it goes to the second one and it says, does this one match? Yes, so we get a 200 okay, and we route our request. So what happens if we get a request for a path that doesn't exist? So the router will say, well, okay, first path, it doesn't match. Second path, again, it doesn't match. Third path, doesn't match. Fourth, again, doesn't match. And finally, we get a 404 not found. And I went and highlighted this, and this slide took forever because really the process to do that takes forever. It actually takes a really long time for the CPU. And the question is, how long does this processing time take? Like, how long does it take to do this particular algorithm? So let's say we have a variable r, where r is the number of routes that we have in our system. Now, let's say we have a variable x, which is the time it takes to do a regular expression comparison. We don't know what that time is. It doesn't really matter. We just know that it takes some time. So the time that it takes to do all of these in the worst case scenario when we have a 404 is r times x. It's easy to see that. Now the question is, can we do better than that? Can we do better than r times x time? And the answer is yes, we can. Otherwise, I wouldn't be here talking to you. I would be at home crying because I would be too slow. So the way that we do that is with parse trees, automaton, finite state machines. And we're going to take a look at each of these particular things that make up our router and make the pattern matching work. The first thing I want to look at is parse trees. And we're going to look at it from the perspective of a regular expression. So first we'll look at regular expressions, and then we'll see how that translates over into Rails routes. So let's say we want to parse a regular expression. We have a regular expression that looks like this. Everybody should be familiar with regexes that look like this. A or B, 0 or more of them, followed by ABB. Now if we parse that out into a parse tree, we have something that looks like this, and there's an error in this graph, but that's okay, we can talk about it later. What the circle nodes mean is that we have a concatenation. So that means we have one character that follows the other, right? So the left side follows the right side, or the right side follows the left side. And then we have down at the bottom our OR nodes, so left or right. And then we have the star, which means everything below me is 0 more times, so optional, right? Now we can do a very similar thing with Rails routes. In fact, we can do exactly the same thing with Journey. So Journey has a parser, and we just instantiate the parser and say, okay, parse this route, and it passes back a parse tree. We get an AST, and we can just output that text dot file and then send that into GraphViz, and we get this output that looks like this. So we can actually get our parse tree out of Journey. So we have a parse tree. We can also say to string on the parse tree and actually get back the original. So, we can get back what was fed in, and we can say to regular expression too, so we can get a regular expression back. What's interesting is since we can convert this into a string, we can actually feed that string back into the parser, which will be interesting in another couple slides. So let's say we have a whole bunch of these routes. We can actually take all of these routes and combine them with an OR node. So let's say we have a couple of these routes here, and we actually want to say, well, we want to match this one or this one. So we combine those two with an OR node, and we can output the dot file for that. And we can see it looks like this. So we have the left side and the right side, so two different routes that we can match, or two different paths. But I mentioned earlier that we can output that as a string and actually parse the string that was output. That means that there's a secret feature, which is that we can parse pipes and say, well, we have OR nodes, but this is a super secret feature. Please don't use it. I will find you and come to your home, and hopefully you'll cook me asado. So the next thing I want to look at is automaton. Let's say we have our regular expression that looks like this. Now what an automaton is it's a directed graph, where a directed graph that lets us match this particular regular expression. So let's look at this graph. This is the graph for the regular expression that we saw. It's a state machine, where we always start at state 0, and we read in a character and we follow the graph. And we just keep following the graph until we get to a point where there's no more input. Now if we end up on this state that has the double circle, that means that we had a match. So let's say that our input string is this, BAABB. So we'll look at an example. We start out at state 0, we haven't read anything in, we read in the first character and it's a B, so we go back to state 0. We read in an A, so it goes over to state 1. We read in another A and it goes back to state 1. And then we just read the BB, and I didn't want to walk through all of them, and we end up on state 3. And it's double circled, so we know that this string is a match. We matched it. Okay. Now let's say that our input is AAB. This is how the state transitions would look for that particular input, and we end up on state 2, and that's not double circled, so it doesn't match our regular expression. And what this graph is called a deterministic finite automaton, or a DFA. And the reason it's called that is because each of the edges on the nodes are unique. So there's no ambiguity about which way that we're actually going to go through the system. There's only one path. And we can actually build this data structure in Ruby, and it's insanely easy. So this is the entire graph that we saw before. It's just a hash of hashes, where we have, on the left side, we have the state that we came from. In the middle, we have the character we read in. And on the right side, that's the state that we're heading to. Okay, so that's the whole graph that we saw before. So let's say we want to simulate this. And what I mean by simulation is that we want to actually walk the graph. What does the Ruby code look like for walking the graph? It's actually incredibly easy. It looks like this. So we say we have a simulator, it takes in that DFA, and it says, okay, simulate on some symbols. We start out at state 0, and then we read all the symbols until we have no more left. And we say, DFA, for the current state, tell me what the next one is given this input character. And it returns a state, and we just keep using that over and over until we run out of input, and we're done. But the one thing we're missing here is this move function. We don't know what the implementation of that is. And if we go over to the DFA and look at the implementation, it's this. It's just a hash lookup. That's all we do. We say, okay, from to, from, read in symbol, returns the 2. That's it. So if we run this in IRB, we can see, okay, here's the simulation of that graph that we looked at earlier. Given the input BAABB, we're on state 3. We know it's a match. The other input, we're on state 2. It's not a match. Now the time for running this simulation is ON, depending on the string length. And it's always ON, no matter how large your graph is. So whatever the size of the string is, that's how long it'll take. Yeah, I like ON time. The space is S plus T, the number of states plus the number of transitions. So we're bounded by memory, but that's okay. So the next thing I want to look at is a non-deterministic finite automaton. And what those are is it's similar to the graph that we looked at before, but the edges are not unique. Okay, we can have multiple edges where it has the same value for the transition. And the other interesting thing is it has nil edges. And what I mean by this is it can do a transition, it can go to the next state without actually reading any input. So the problem with this is you can't necessarily tell the direction that you're going to go through the graph. So how do you walk that graph? How do you simulate it? And the way that you simulate it is you have to actually walk all possible paths at the same time. So let's say we have this regular expression, A or B. This is the non-deterministic version of this particular regular expression. So we say, okay, we start out at state 0, but it's possible that we can read no input and move to a next state. These E's are nils, actually. So when we do that, we say, okay, let's look at the nil closure. That's what we call the nil closure. So now when we read an input, we have to consider 3 states, 0, 2, and 4. Now let's say we read an input A. Well, A can't transition off of 4, but it can transition off of 2, so we go to 3. But 3 has a nil transition down to 6, so we don't have to read in any more input, and we have a match. So the main difference here is that we have a list of possible states. And the storage for that looks like this. It's also a very simple data structure, and you'll notice mainly the difference with this data structure is our right-hand side is a list. So we say, given this state, given this input, what are the states that we could transition to? And the simulation looks almost exactly the same as our DFA, except that we're dealing with a list. So we'll say, okay, give me all the nil closures off of state 0, read in all of our input, and we just keep getting lists of states and going through the simulation. Our move function is similar to our previous one, except that you'll note that the move function returns a list. So when we simulate that, we'll see, okay, we simulate A, we get back a list, which is 6. That has an accepting state. We say it's a match. B is okay, but if we do BB, no match. C, again, no match. And what is the time for this? How long does this particular match take? Well, it takes R times X, where R is the number of operators and X is the string length. And this isn't really awesome. You'll notice this time is actually the same as our naive approach, which was just testing every single regular expression that is in the system. And in fact, in the worst case scenario with a non-deterministic state machine, that's exactly what it is. So why do we care about NFA? We just saw a DFA before. We could match in ON time. Why do we care about NFA? And the reason we care about it is because NFA construction is very easy. It's really easy to make a graph that's an NFA graph. And the way that we do that is, let's say we have a parse tree that looks like this. We can recursively process the parse tree and generate an NFA transition table from it. So let's say we're at one of these cat nodes, like this slash and articles, that cat node above it. What we do is we construct a mini state machine that looks like this. This is our mini state machine for just those nodes. So 0 to 1, we have to match a slash for that to match. And we move up our parse tree, and we say, okay, well, we have slash and articles, and we combine those together. But let's say we run into maybe an optional one. So we have some brackets. The state machine that we produce for that is, well, we have, okay, we start out with 0, and then we have a nil transition over to the ending state, and then we have a 1 and a 2. And in the middle, we don't know what that is. We don't know what happens in the middle, but that's the best thing about creating these NFAs is we don't need to know, because we just say, well, you know, whatever was lower in the parse tree, that's what's in the middle. I don't care. And it doesn't need to know. It doesn't need to know the context. So if we do that and run it against this particular route, we'll see this is our parse tree. That's what it looks like. And we can produce these with Journey like this. It's really simple. We say, okay, parse this, generate an NFA, give me back the transition table, and we can print out the dot file. And that's actually the graph that we saw in the previous slide. So we can say, put out the dot file, there it is. So Another interesting aspect about NFA tables is that we can convert them into DFA, which means that we can take these tables that have R times X time and convert them into tables that have ON time, which is what we want. And the way that we do that is we eliminate those nil transitions and we collapse all of the duplicate edges. So we process the tree. So given this particular tree, if we eliminate all of the nil edges in this tree and collapse all the duplicates, then we'll end up with a tree that looks like this. And you'll notice that this particular tree has two final states, two circled states. But we can process it in ON time. And Journey lets us do that too. So we say build our NFA table, and we say, okay, give me back the generalized table and print out the dot file, and that's what we saw on the previous slide. Another cool thing is that we can actually take the AST and go directly to DFA. So we say, all right, give me this GTG, give me back the transition table, and now we're at a DFA table. So the important thing to take away from this is that any NFA can be converted into a DFA. So we can always say, all right, let's take this R times X operation and convert it into an OX operation. And I like that. So, another interesting thing that we can do is we can take these automata graphs and convert them back into regular expressions. We don't need to do this for the router. I just think it's totally nerdy and awesome. So we have this graph, and we say, well, let's convert it back into a regular expression. And the way that we do that is we just start collapsing these states. And we say, well, let's combine the first two. And now this edge is actually a regular expression. Just keep in mind that that edge is a regular expression. We combine these again. Okay, well, now we have two regular expressions. Combine them again, and now we have one single regular expression. And this type of tree is called a generalized transition graph, or a GTG. So when we process these resources, say resource users, and we generate this tree, we'll see on the edges here, I know it's kind of hard to read, but we'll see on the edges that those are actually regular expressions on the edges, because we get regular expression input from Rails. So the trees that we actually produce are GTGs. So that's what's produced under the hood. Our plan is to take all of the routes, combine them together, produce a DFA, and simulate in ON time. So that's what we want to do. Now, routing to the future. I want to talk about some of the new features that I added to the router. I want to talk about JavaScript simulation. So we saw earlier that the data structures that hold these particular tables are very simple. Just a hash of hashes with numbers and strings. Really, really simple. And because the data structure is so simple, it was really trivial to write a function that converted it into JSON. So we could take that transition table and convert it to JSON. Okay? So let's say we do that. Then let's say we take that graph, the graph that we saw of the routes, and one interesting feature of GraphViz is that we can actually take that graph and convert it into SVG. So let's say we do that. We convert the graph into SVG. Now let's say we write a tokenizer in JavaScript, and in fact this is the tokenizer. This is all of it. And we rewrite our simulator in JavaScript, which we also saw was very easy code. This is all of it. And we combine that with d3.js and mash all of those into one HTML page together, and we'll come up with something like this, where we can enter in a route and then actually see it visualized through the state machine. So we can take the routes in our Rails system and say, well, given this particular path, how does the state machine handle moving that through our system? So there we go, on /users, we can see all of that together. Now you can get this today if you run against edge rails. Am I done there yet? I mean, moving my mouse around. We can get this on edge rails if you do this. So if you generate your web application, you can get that output with your application today. The API is insanely terrible if you haven't noticed. Just like, it might not work in the future, so don't like report. I mean, I will continue to have an API that allows you to do this, but this particular crap API may not be supported in the future. So another interesting thing we could do is since these data structures that store our routes are so simple, we should be able to take the routes.rb file, process them, and actually marshal that data out to disk. So let's say in between restarts on your system, well, the routes.rb file hasn't changed, so what's the point of processing it again? Why don't we just load all of those data structures off disk and be done? So we pay 0 time for parsing the routes.rb file. Another thing we can do is, well, since we have this state machine, we know every single route in your system. We know every possible route. So we can suggest tests to you. We can even do test coverage. So let's say that simulator keeps track of all of the routes, all the paths that it went to. It can say, well, okay, you went to all of these paths, but you're missing these. We can also have usage heat maps. So we can say, well, okay, let's output that graph, but let's color it and say, well, okay, you go to this route very often and not this one. Another awesome thing is we saw, well, we can go from AST to NFA to DFA back to a regular expression, which we know we can turn into an AST again. And what that means is that we can raffle scale. Absolutely raffle scale. And the way that we do that is we can take our DFA and we can turn them into a YAC grammar. Or we can turn them into a rack grammar. Or we can turn them into a raggle grammar. So we can actually have our routes turned into C and compile our routes for raffle scale. So I want to leave you with a couple open questions. The first question is our GTG deterministic? So given that we have this GTG, those edges that we produce, are they deterministic? Are those edges unique? And unfortunately, the answer is no. So let's say we have these two routes, users new or users ID. Here is the graph that's generated from it. And if we go look at the right side there, on one edge we have the string new. And on the other edge we have this regular expression. You don't need to understand the regular expression, but the annoying part is that this regular expression also matches the string new. It's insanely annoying, especially when I found this out rewriting this router. I was very annoyed. So the problem is, you know, if we have a regular expression that represents that, when we say in Ruby, okay, new, does it match this regular expression? Ruby comes back to us and says, ah, yeah, it matched that regular expression. It matches. That's great. But we don't know which side it matched. We have no idea. So that means that even though we have these GTGs, we still have to simulate all paths simultaneously. And we saw that the time for doing that sucks. It's terrible. The question is, can we make it deterministic? And I think the answer is yes. If you look at automaton theory, you'll find that regular expressions can be represented as sets in set notation. So we can say, well, let's represent the string new as a set, and let's represent this regular expression as a second set, and let's rewrite our graph. And say, well, that edge is L1, our new, and the other edge is L2 minus L1. But the real problem is it worth our effort? I took a survey, I don't know, a few months ago and had about 90 people, or route files from 90 different applications sent to me. And I found that, from this research, I found that, well, yes, we don't have a deterministic graph, but most of the times those conflicting edges are very few. So the interesting thing with this GTG is that we're actually bounded. So the lowest bounds is ON time, and the upper bounds is OR times X time. So we're somewhere in between there. And most of the time, we're very close to ON, down at the bottom. So is it really worth our effort to go in and start parsing regular expressions and turning them into sets and doing all these set manipulations? I'm not sure. I'm really not sure. The other question is, we saw that we can do this entire circle and actually output YAC grammars and raggle grammars and raffle scale our routes files to something written in C. But are we really spending that much time in our routes files? Are we really spending that much time processing routes? I'm not sure. So again, the question is it worth our effort? That's what I want to leave you with. Think about it. Tell me the answer, because I don't know. And with that, I want to say thank you.
¿Preguntas?
If we have time, I'll take questions, and it doesn't have to be about this at all. The asado was delicious. Trust me. Yes. I'm going to Uruguay after this. I don't know what they're going to do. Oh. It's on. Yes.
¿It's working?
Yeah.
Sí, solamente si tenés alguna estimación de qué versión de Rails va a incluir este nuevo router.
Oh, yeah. This router is in master and it will be in Rails 3.2.
Gracias.
So it's me again.
Yes, Luis.
So you say it's going to be on Rails 3 something?
3.2.
3.2.
Yeah.
Okay. It's going to be the C version, or it's going to be the compiled version, or it's going to be the pure Ruby version?
Pure Ruby. Yeah, pure Ruby. If we ever figure out that it's, like if we can ever determine that it's actually faster to produce C, then we'll do that, but I have a doubt.
Okay, thank you.
Hi.
Hello.
Currently, routes also support constraints. You can even pass dynamic constraints, your own object to match for those. Should that feature be killed? Or?
I think so, yeah. So, yeah, if we have that feature, that's a huge problem. If we have that feature, you can't produce deterministic graphs. So we can't know what somebody's going to test against. And let's say, for example, what? Shoot, there we go. Okay, so let's say people are allowed to pass their own regular expressions into the router and say like, well, okay, I want this. And believe me, when I surveyed the routes, there was some crazy stuff. But people are allowed to provide their own regular expressions. And the problem with that is that they can backtrack. So they actually move backwards through the match. And it's impossible to integrate into this system that I've written unless we actually parse the regular expressions themselves. And I just don't want to do that. So what I found is that only 5% of all routes used custom stuff like that. So 5% of all paths actually had that custom stuff, so fairly low percentage. But what was bothersome to me is like I wanted to kill the feature, but unfortunately, like even though it's only 5% of the total routes, about 30% of the applications use that feature. So many applications use the feature, it's just that they don't use it very often, and please don't use that feature. If you can avoid using that feature, your router will be faster. I mean, go ahead and use it, but just know the consequences.
Could the routing system be made pluggable the way ORMs are pluggable in Rails 3, so that if you did want to do something really crazy, you could swap that in and use it instead? Yeah, absolutely. So right now, unfortunately, the previous router was, I feel extracted prematurely, is very coupled to Rails, and unfortunately for me to get mine to be backwards compatible, it is not quite as coupled, but still coupled.
I would like to get it to that point, but first, one thing I want to do is, like, we've been talking about this and it matches paths, so we saw it always matches paths, and I don't like that. I don't actually want it to match just paths. I want it to match verbs along with the paths, so that we just read in the first line of the request and feed that straight into the state machine. And ideally, we would have just something that was like, a really simple API that was like, okay, provide your router and, do whatever you want to, and I'm just going to feed you a string. So we'd have like, 2 methods or something like that. I would really like to see that. So not for 3.2, but in the future, yes.
Hey.
Hello, where are we? Oh, hey.
Hey.
Hello.
So you're saying you don't want to parse regular expressions, but couldn't we just have, in Ruby, do something inside the Ruby code to have an AST generated from the regular expression itself?
So you mean like somehow use Ruby's regular expression engine to get an AST?
Yeah.
It's probably possible, but that would mean a C extension.
Mm-hmm. Yeah.
And I don't want to add any C extension. I don't want to add any C extension dependencies to Rails.
Yeah, that makes sense. All right. Thanks.
Hola, Aaron.
Yes.
Gracias por la charla. No
Thank
soy
you.
usuario de Rails, pero me parece interesante preguntarte qué otras cosas se van a hacer o se pueden hacer para acelerar el tiempo de carga, el tiempo de buteo de una aplicación en Rails.
Yeah. Well, the first thing you should do is if you're using Ruby 192, upgrade just immediately. Just upgrade and it'll be faster. Use 193. So, unfortunately, right now, routing is only part of it. The other part is file loading, and I'm not exactly sure what to do about that. Unfortunately, today it's a giant yak shave. Is there a Spanish translation for yak shave? I'm not. What is it? Quilombo. Okay. Quilombo. All right. So anyway, it's a giant yak shave. Right now, I'm going to be adding dtrace probes, or I have dtrace probes added to Ruby so that I can profile this particular problem. And I just need to add more probes to it so I can figure out the issue, but it's definitely on my list of things to do. I guess I didn't mention this earlier, but I work for AT&T and I work on open source all the time. And specifically I work on Rails because we have a lot of Rails developers. So it's important to me to make their development time efficient as possible. So I'm very focused on load time. I can't tell you specifically what we're going to do to improve it, but it absolutely needs to be improved. I'm sorry I didn't completely answer your question. That was totally like incomplete.